We're Team 1070. I'm Reid, working with Henry and Kieran. This is SCUDEM Problem C, standing against a mammoth. To start our problem, we were looking at close point spears during prehistoric times. There were two main conjectures that have been posed about how these spears are used in hunting. The first was that spears were thrown at large animals. This allowed for distance management at the cost of lower damage to the animal. The second conjecture was that spears were braced against the ground for large animals to charge into, causing greater risk to the individual but greater damage to the animal. Our goals were to decide which of these conjectures were more effective using differential equations and kinematics. We also wanted to determine the speed of a charging animal that would represent a similar level of damage to that of a thrown spear. And we also wanted to weigh aspects of a close point spear that would be more effective as a thrown weapon versus a braced weapon.
Now to get into the modeling. For starters, we had to make some assumptions. First, we assumed that the air resistance on the spear while it's in the air is negligible. The spear is always accurately thrown. When we have a braced spear, the animal charging the spear does not react on contact, and a braced spear is more risky than a thrown spear, but also more lethal to an Arctodus. The reason we are mentioning an Arctodus is because in our research we found data shown in this table for an Arctodus, and we decided that that was going to be a more interesting project than thinking about a mammoth. The two rows highlighted in this table are the two rows of data we use later in the project. So our initial approaches included that we determined depth of piercing, safety, and total kinetic energy were important for the effectiveness of each conjecture. For our thrown spear, we had to make some assumptions as well as using kinematics to determine what was useful. And for our brace spear, we mainly relied on assumptions to get started.
So first we'll go over the thrown spear conjecture as seen here. We had to make some kinematic assumptions for the thrown spear. First of all was that it's thrown from a starting height of 2 meters, and then where it punctures the Arctodus is 1.5 meters. The velocity of the spear is 16 meters per second, which was seen in the table earlier, and the release angle is 45 degrees, which maximizes total potential distance. So next, getting into the actual kinematic equations for the thrown spear, we start with this equation here, and solving for initial velocity, we get 16 over root 2 in both the x and y direction. And then plugging that back in, we end up with a final velocity of 11.7 meters per second, which is the moment that it punctures the Arctodus. So continuing with the equations, we derive a time of 2.35 seconds, and then plugging that back in, we end up with a maximum potential distance of 26.47 meters. So using our final y velocity of 11.7 meters per second and our final x velocity of 16 over root 2 meters per second, we end up with an overall final velocity of 16.3 meters per second, which represents the velocity of the spear as it made contact with the skin of the Arctodus. Next, we have the brace spear conjecture, which you see here. The assumptions for the brace spear are that the velocity of the Arctodus is 9 meters per second and the mass is 400 kilograms. With negligible external factors, thankfully we can just sub this into the differential model and go from there.
Now getting into our actual model for piercing, we first assumed that the resistive force on the spear was equal to some damping constant C times the velocity P prime, and that the total force acting on the spear was equal to this resistive force. Using this and assuming a negligible spring force, we ended up with the second order differential equation, m times p prime minus the resistive force equals 0, as there are no external factors. Substituting in our velocity for p prime, we got the first order differential equation, mv prime minus cv equals 0, which we solved using the integrating factor method to end up with the solution velocity equals v initial times e to the ct over m.
So now that we know that our velocity is equal to velocity initial, e to the ct over m, we want to sub back in our p prime and solve for p. Integrating p prime, we found that p is equal to v initial m over c, e to the ct over m plus a constant. Immediately we notice that our initial momentum is equal to v initial times mass. To solve for our constant, we use our initial condition that our pierce distance is 0 at time 0, which gave us a constant of negative v initial m over c. Summing this back into our model, we found that our final piercing model for piercing distance was v initial m over c times the value e to the ct over m minus 1.
Additionally, we wanted to incorporate the kinetic energy into our model, as we know that kinetic energy has a direct relationship to the amount of damage done by a spear. To do this, we use the fact that p prime equals our velocity at time t, and we can solve for velocity in the kinetic energy equation to get p prime equals root 2ke over m. We can then plug that back into our differential equation model, and we end up with the kinetic energy at time t equals our initial kinetic energy, which is v naught squared m over 2 times e to the 2ct over m. With this information, we can now answer the second of our three goals, which was what speed would a charging Arcturus have to be moving to mimic the damage or lethality of a spear thrown at 60 meters per second. To do this, we can simply sub in the kinetic energy of a spear going 60 meters per second, that being 102 joules, and the mass of the Arcturus being 400 kilograms into our equation. And we end up with a velocity of 0.714 meters per second that the Arcturus would have to be moving to mimic that lethality of a spear. And this is extraordinarily slow, around 1.6 miles per hour. Note we have a slight mislabeling error here. The y-axis on both these charts should be kinetic energy in joules, as what we next did was plot our kinetic energy versus time. Note we have a vast difference in the kinetic energy in the thrown spear system versus the brace spear system, as well as the kinetic energy in the thrown system decaying nearly 20 times faster than that in the braced spear system.
So now that we have the modeling portion done, let's get into some of the actual results. First, looking at the thrown spear, we have the given modeling equation that you see in the top, plugging in the known values in the top right, which are the initial velocity equals 16.3 meters per second, the mass equals 0.8 kilograms, and the damping coefficient equals negative 90 kilograms per second, which we found by the ansatz that the spear would puncture approximately 14 centimeters into the animal. We have the given equation that you see underlined at the bottom, which produces the graph through Mathematica, as you can see on the right.
Moving to the brace spear, we know that our initial velocity multiplied by mass is equal to our initial momentum, and then using conservation of momentum, we can sub in the bear values instead of our spear values. Next, we wanted to find our damping constant, and we used outside research to do this. Based on this research, we found that in boar hunting, a boar would charge the full length of the spear as long as the spear did not have a crossguard. Assuming that these closed point spears did not have crossguards as well, and that the bear would do the same thing as the boar, we found our damping constant, and we made a plot of our pierce distance as seen here. Finally, moving to some conclusions, we'll look at some pros and cons of each conjecture. Starting with throwing the spear, it's obviously a lot safer for the individual as we have a larger range of about 26 meters. But we also have the cons. It's clearly a lot less lethal, and there's risk of inaccuracy, and there's a chance that it will break without doing any damage to the bear. On the other hand, we have bracing the spear. We have a lot more damage, and it's a lot less likely to break without doing damage to the bear. Cons on this side, it's a lot more dangerous and it's a lot more difficult to set up as it's difficult to corral the bear into the spear. Here are some relevant values to back up what we established on the last slide. We have our maximum range of the thrown spear as well as the maximum pierce distance of both the thrown and the braced spear. All of this together led to us believing that the braced spear was the correct conjecture, as the pros of the thrown spear do not outweigh the pros of the braced spear.
There are a few large problems with this model. First and foremost, we had to make a lot of assumptions on different values, the greatest of which being how deep the spear would pierce into the animal. Additionally, we did not incorporate the spring force of the bear's skin, which in reality would be non-negligible. We also assigned arbitrarily value to safety versus lethality of each conjecture, and eventually ended with lethality being more important than safety. However, maybe this was not the case in reality. We also estimated a damping coefficient, which was most likely not the correct value, but was the best that we could get to. And finally, we did not take into account the fact that Clovis point spears often break during penetration, and therefore increase the deceleration of the spear into the animal. Here we have listed a few future directions that we could take this model, such as accounting for piercing the skin and finding an appropriate forcing function to model the animal slowing down on the spear.
Finally, moving on to spear shape, a Clovis point is wider and not exceptionally sharp, which is ideal for a brace spear because of the increase in damage and sturdiness. This is not ideal for a thrown spear, as that would be better when sharper due to deeper penetration and force focused on a smaller area. This is further evidence that a Clovis point spear was likely braced in prehistoric times. In terms of spear length and weight, heavier and longer spears would be better when braced, and shorter and lighter spears would be better when thrown. And this concludes our modeling project.